We will wait for a few more minutes so that more students, if they are joining, they can join, and then we will start. Hello everyone, a very good evening to all. Once again, I welcome you all for this fourth interaction session on the course Atomic and Molecular Physics, which is being flowed by NPTEL this January 2026 session with course code NOC 26 PH18. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today, since it's our fourth interaction session, so you will cover a few sample problems that will be based on the week 4 course content of the or week 4 lectures of the course, and we will solve a few problems that will be again based on these lectures, and those problems will help you in solving this year's assignments as well as in your exam preparations. So before solving the problems, let's discuss a few things briefly about the topics or concepts that were covered in this week's lecture. So basically, if you talk about week 4, which is lecture 16 to lecture 20. So the continuation of the structure of atom was discussed. Like last week, we discussed the concept that was covering the topic related to Bohr's theory, as well as the drawbacks of Bohr's theory, which again led to Sommerfeld's modification to those theory. So in continuation with that, the concept related to structure of atom was discussed. Structure of atom, then space quantization, which is basically orientation of angular momentums. Like the energy levels are quantized, so the orientation of angular momentum is again quantized, and also the orientation of angular momentum is also quantized. So orientation of angular momentum is also quantized. So basically, it says the angular momentum can be oriented in some arbitrary directions. So depending upon the values of there are different quantum numbers. So this space quantization led to another quantum number which we called as for azimuthal quantum numbers or orbital angular momentum quantum number, we call it as L, and for spin angular momentum quantum number we call it as S. So due to different orientations, we got new quantum numbers which is ML corresponding to L. We got ML and corresponding to S, we got MS. So this is uh, the space quantization concept. So the space quantization was also verified experimentally, which also the same experiments also proved the presence of electron spin, which is called as Stern-Gerlach experiment. So Stern-Gerlach experiment was also discussed. Stern-Gerlach experiment. So it was performed in 1922, and it proved it discovered electron spin, and also proof of space quantization. So now let's briefly discuss the Stern-Gerlach experiments. So this is the experimental setup for Stern-Gerlach experiment. So this one, as we can see, it is silver atom source. So the silver atom is heated in an oven, which produces the beam of neutral silver atoms. So we know what is the atomic number for silver. So atomic number of silver is how much? It is 47. So silver, it is 47. So if you arrange it, how we can arrange? So silver, if you arrange 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 4d10, and 5s1. So silver has only one electron which is in s orbital. So why silver was chosen? Because it has only one electron and also that is present in s orbital, and we know for s orbital the orbital quantum number or azimuthal quantum number, it is 0. So it has no orbital angular momentum. But as we can see from the experiment, so what we did in the experiment, the silver atoms were heated in an oven, then it was collimated to form a beam of silver atoms, and then that silver atom beam, it was passed through a non-uniform magnetic field. So why non-uniform magnetic field? Because when the magnetic field is non-uniform, if some atom, some a particular species or atom, here in this case it is silver atom, if it has angular momentum or magnetic angular momentum, then it will experience force. So that will lead to bending of the beams. So the force is given by del mu dot b. So in a non-uniform magnetic field, an atom with orbital magnetic moment, it will experience force. So that's why non-uniform magnetic field was produced. As you can see here, the shape is like this. So here the field is high and here the field is low. So the field through which the silver atoms were passed, the field was non-uniform, and due to this non-uniform field, the silver atoms experience force, and it was found that so this 4 and 5, they are the projections of the silver atoms in the screen. So the detector plate basically shows how the silver atoms are being deposited. So when there was no magnetic field, then we found that it is a straight line. But however, in presence of magnetic field, we found it has two different orientations. So basically, since s is equals to, so for s, l is equal to 0, so it don't have any orbital angular momentum, but due to the spin motion of electron, so that led to the discovery of electron spin. So it was found that electron has another intrinsic property which is related to the spinning of electron around its own axis, which is called as spinning motion of electron. So that led to the discovery of electron spin. We assigned a new quantum number, that is spin quantum number. Then from that spin quantum number, similarly, uh, another concept, that is space quantization, that was also proved. So basically, due to space quantization, spin in the for electron, so due to space quantization, there are two spots. So if you, there are two projections, so 2s plus 1 is equal to 2. So if you calculate, s is equal to half. So it was found that for electron, s is equal to half, because there are no orbital quantum number involved for silver atoms for the last electron of the silver atom. So again, after Stern-Gerlach experiment, we can say that we have all four quantum numbers. So one is principal quantum number, which is n, and it is 1, 2, 3, 4, like that. Then azimuthal or orbital angular momentum quantum number, azimuthal quantum number. So this is L. So L has value from 0 to n minus 1. Basically, azimuthal quantum number came into picture during the Sommerfeld's modification, where the theory that was given by Bohr, it said that the atoms are in an atom, electrons are orbiting in a circular orbit, but Sommerfeld had another Sommerfeld introduced another quantization, and that led to elliptical orbit. So due to the elliptical orbit, the semi-major, semi-minor axis came into picture. So that can lead to introduction of new quantum number. Then the third is in presence of magnetic field. Then when an atom is present in a magnetic field, then its angular momentum gets oriented. So depending upon the direction of magnetic field, the angular momentum orientation, that led to another new quantum number, which is called as magnetic orbital magnetic quantum number and spin magnetic quantum number. So magnetic quantum number related to orbital, which is ml. And what is the value of ml? So ml has 2l plus 1 values. So it starts from minus l, goes up to 0, and then plus l. And then this is spin magnetic quantum number. Spin magnetic quantum number, which is called as ms, which has two values, plus minus half. So l, depending upon the value of l, we have different orbitals. So orbit is 1, 2, 3, 4. These are orbits of stationary states, because as long as atoms are electrons are present in that orbit, energy does not change. So they are called as stationary states. Then coming to orbitals, we have for L equal to 0. For L equal to 0, we have S. For L equal to 1, we have P. Then L equal to 2, it is D. And then it is F. So we have different orbitals. Then depending upon the orbitals, we can assign the quantum numbers for electrons. Then also a few more. Let me add another slide. So a few more concepts are also covered. So this introduction of quantum number, that basically led to fine structure of hydrogen atom. And the fine structure of hydrogen atom is due to LS coupling. So LS coupling concept was also discussed, and those LS coupling, the orbital, the different energy states were discussed, coming into in different energy states. Basically, they came into picture. So in order to represent them, we also discussed spectroscopic notation. Spectroscopic notations, which is called as 2s plus 1 Lj. So 2s plus 1 is multiplicity. Depending upon the value of L, it can be, so this is orbital and this is total quantum number. So this is the concept of LS coupling and spectroscopic notation. So now we will solve a few problems that will be based on the concept that was discussed in this week's lecture. So let's discuss first question of today's interaction session, but let me check if there are any other students present or not. Okay, so then let's start our discussion. Let's continue our discussion. So question number 1 says the ground state term for hydrogen like atom. So hydrogen like atom means it has only one electron. So this is called as hydrogen like atom. So hydrogen like atom, that means it has one electron. So what are the examples? Helium plus, lithium 2 plus, beryllium 3 plus. All these are called as hydrogen like atoms, because since helium, it has two electrons, but helium plus has one electron, so they have only one electron. So we need to find out the ground state term for those atoms which has only one electron, and the options are option A 2s 3 by 2, option B 2s half, option C 1s half, and option D 2p half. So these are the four options. I'll give you a few minutes to try to determine what will be the ground state, and then we will discuss. So now let's discuss. So hydrogen like atom, like already said. So hydrogen like, that means one electron. Now for one electron, what is the value of one electron, and it is present in ground state. So for ground state we know n equals to 1. Then what is the value of L? L we know L has values which is 0 to n minus 1. So 0 to n minus 1 means, so 0, n minus 1 is 1 minus 1 again 0. So L is 0. So L is 0. And then what will be the value of S? We know for electron S is half. So S is half. Now let's remember. Now remember the spectroscopic notation, which is 2s plus 1 L and J. So when S equals to half and L equal to 0, what will be the value of? So since it is only one electron, then what will the value of J? So J will be L plus S to L minus S, and there will be vector addition. So 0 plus half, 0 minus half, it is again half only. So J is half. So we got L is equals to 0, S equals to half, and J equals to half. So if that's the case, then what will be the spectral notation? So 2s plus 1, it will be 2 into half plus 1, which is 2. Then L equal to 1, L equal to 1 means S, or sorry, L equal to 0 means S orbital. Then J is half. That is the total angular quantum number. So it will be 2 S and half. So the ground state of hydrogen like atom, it will be represented by the spectroscopic term 2s half. I hope this is clear to everyone. Now we will move to question number 2. So question number 2 says, write the values of spin quantum number, orbital quantum number, and total quantum number for the spectroscopic term 4d 5 by 2. The options are S equals to half, L equals to 2, J equals to 3 by 2. Option B, S equal to half, L equal to 2, J equal to 5 by 2. Option C, S equals to half, L equal to 3, J equals to 5 by 2. Or option D, S equal to 3 by 2, L equal to 2, and J equal to 5 by 2. So I'll give you a few minutes and then we will discuss. So now this question is exactly opposite of the previous question. In the previous question, we first decided what will be the values of S, L, and J, and then we wrote the spectroscopic term. And then, but here the spectroscopic term is given, which is 4D 5 by 2, and we need to compare it to the spectroscopic notation 2S plus 1 L and J. So in that case, what we obtained, so if you compare these two things, so we found 2S plus 1 is 4, L is represented by D, and J it is 5 by 2. So straight from this we determined one quantum number, which is J. So J is 5 by 2. If you see these three options, we have J equal to 5 by 2. So option 1 gets cancelled out. So then we need to obtain what is the value of S and what is the value of L. So so we know 2S plus 1 it is 4. So 2S is 3 and S is 3 by 2. So again we got S and we got J. J is 5 by 2. So out of so since we have S is equal to 3 by 2 and J equal to 5 by 2, now let's determine L. So L it is D. We know for L equal to 0 it is S, L equal to 1 it is P, L equal to 2 it is D, and L equal to 3 it is F. So L is 2 since D is present. So but how now you can see, since L is 2 and S is 3 by 2, there can be multiple J values. So what will be the value of J? So J is L plus S to L minus S with one increment, which is basically called as vector addition of the two numbers. So 2 plus 3 by, sorry, 2 minus 3 by 2, it is half. 2 plus 3 by 2, basically 4 by 2 plus 3 by 2, it is 7 by 2. So half plus 1 3 by 2 plus 1 5 by 2. So there will be 4 J values, 1 by 2, 3 by 2, 5 by 2, and 7 by 2. So there can be 4 levels by the combination of S is equal to 3 by 2 and L equal to 2. But here only one state was given, which is J equal to 5 by 2. So the correct option is S equal to 3 by 2, L equal to 2, and J equal to 5 by 2. So the correct option is option D. So I hope this is clear to everyone. Now we'll move to question number 3. Question number 3 says, let, according to Sommerfeld theory, the energy of an electron in the nth Bohr orbit with azimuthal quantum number k without considering non-relativistic correction is E, and considering relativistic correction it is ER. Then what is the relationship between E and ER? So A, E equals to ER, option B, E less than ER, option C, E greater than ER, and option D, E may be greater than, equal to, or less than ER depending upon the value of N. So these are the 4 options. So it's a very good question. So we need to consider the Bohr-Sommerfeld modification to the energy of the electron, and then we need to see when we are applying non-relativistic correction, then what will be the change in energy, whether the new energy value that we obtain it will be greater than, less than, or equal to the earlier energy values. So I'll give you a few minutes and then we will discuss in details. So what is the energy value? Uh, so if you talk about the relativistic correction, ER is minus RHC by n square minus RHC by n square, then alpha square, then there is correction n by k minus 3 by 4. So if you take minus RHC by n square as common, it is 1 plus alpha square n by k minus 3 by 4. So this is, which is the original expression for energy given by Bohr, which is E. Then it is 1 plus alpha square n by k minus 3 by 4. So now see, let me write it once again. It is ER, which is minus E 1 plus alpha square n by k minus 3 by 4. So now according to Sommerfeld theory, we know n is always greater than equal to k from Sommerfeld's theory. So then n by k is greater than equal to 1. So n by k will be greater than 1 or n by k will be equal to 1. So in that case, 3 by 4, we know 3 by 4 is less than 1. So this term n by k minus 3 by 4. So n by k minus 3 by 4, it will be greater than 1. So in that case, so 1 plus alpha square, it will be greater than 1. So it will be ER will be minus E into 1 plus something which is again greater than 1. So ER will be more negative than E. So ER will be minus E, and there is a value which is greater than 1. So minus 2E minus 3 minus 1.1 like that. So in that case, ER is more negative than E. 1 minute. So ER is more negative than E. That implies ER is less than E. So due to Sommerfeld's modification, suppose this was Bohr's energy, then Sommerfeld's energy level will be a bit lesser. So this is Bohr, then this is Sommerfeld like that. So ER is less than E. So ER is less than E. So option, sorry, ER is less than E. So we need to change. So eraser. So ER is less than E, so E is greater than ER. So correct option is option C. I hope this is clear to you. Now we move to question number 4. Question number 4 says, for the spectroscopic term 6H 5 by 2, write the value of quantum numbers S, L and J. Options are option A, S equals to 5 by 2, L equal to 5, J equal to 5 by 2. Option B, S equals to 3 by 2, L equal to 5, J equals to 5 by 2. And option C, S equal to 3 by 2, L equal to 4, J equal to 5 by 2. And option D, S equal to 5 by 2, L equal to 3 and J equal to 3 by 2. So these are the four options. So this is again pretty much similar to the previous question that we solved. So it is 6 H 5 by 2. So if you compare it to 2S plus 1 L J, we found 2S plus 1 is 6, J is 5 by 2 and L it is represented by H. So we know 5 by 2, if 2S plus 1 is 5 by 2, sorry, 2S plus 1 is 6. So this is 6. So 2S plus 1 is 6. 2S is 5. That implies S is 5 by 2. So now J it is already mentioned. J is again 5 by 2. So now you need to find out the value of L. So when L equal to 0, it is S, 1, P, 2, D, 3, F, 4, G, 5, H. So L is 5. So again, if you see L is 5 and S is 5 by 2, so there will be multiple values of J. So what will be the possible values of J? So L plus S is 5 plus 5 by 2, which is 15 by 2. Then L minus S, 5 minus 5 by 2, it is 5 by 2. So in between we have 13 by 2, 11 by 2, 9 by 2, 7 by 2 and 5. So there are 6 possible values of J. That's why it is 6 here. So this 6 represents what are the possible values of J. So what are the number of, so how many numbers of J are possible? So if you remember, here in this case, it was 4 and we got, there are 4 values, 1 by 2, 3 by 2, 5 by 2 and 7 by 2. So basically this shows the multiplicity, that is there are how many number of labels which are same value of S and same value of L, but they have different value of J depending upon the orientation. So that's why there are more labels that are being introduced, because since J is changing, so there are some change in its energy. So different in energies are different labels are being introduced. So more and more labels means more and more transitions. So there will be fine structure. So what we have got, S is 5 by 2, L 5 and J is 5 by 2. So S is 5 by 2, L is 5 and J is 5 by 2. So the correct option is option A. Now we move to question number 5. So question number 5 says, find the angle between angular momentum L vector and S vector for the spectroscopic term 2p3 by 2. So these are the four options. Option A 45 degrees, option B 65.9 degrees, option C 87.5 degrees and option D 137.3 degrees. So we need to find out the angle between L vector and S vector for which term 2p 3 by 2. So these are the terms for which we need to calculate the angle between L vector and S vector. So it is a bit different from determining the quantum numbers. So we will discuss it in more details, but before that I'll give you a few minutes so that we can try and solve it, and then we will discuss it in details. So we know. So what is the way to calculate the angle between L and J? So we know J vector is L vector plus S vector. Now J vector, J vector, it will be L vector plus S vector dot L vector plus S vector. So if you calculate, it will be L square plus S square plus 2 L vector dot S vector. So this L vector dot S vector, that means L square plus S square plus 2 LS cos theta, where theta is the angle between L vector and S vector. So what will be the expression for L? So you see, it is cos theta will be J square minus L square minus S square. So cos theta will be J square minus L square minus S square divided by 2 L into S. And we know L is given by root over of L into L plus 1 H cross. S is root over of S into S plus 1 H cross. And J is given by root over of J into J plus 1 H cross. So in this case, what is the value of Lj? So in 2p 3 by 2, in 2p 3 by 2, 2s plus 1 is 2, so s is half, j is 3 by 2, and l we know for l equal to 1, it is p, so l is 1. So by putting these three values, we can calculate. So what will be the value of cos theta? So cos theta is j into j plus 1 minus l into l plus 1 minus s into s plus 1 divided by 2 l into l plus 1 into s into s plus 1. So here it will be h cross square, here it will be h cross square, so they cancelled out. So j is 3 by 2, s is half, l is 1. So it is 3 by 2 into 5 by 2 minus 1 into 2 minus half into 3 by 2. Half into 3 by 2 divided by 2 into L into L plus 1. L is 1 into 2. So 1 into 2 into half into 3 by 2. So it is 15 by 2, sorry, 15 by 4 minus 2 minus 3 by 4 divided by 4 into 3 by 4. 4 gets cancelled out. It is 15 by 4 minus 2 minus 3 by 4. So it will be divided by 4. 15 minus 8 minus 3 divided by 3. So 15 minus 11, it is 4. 4 by 4 into 3, so 3. So cos theta is 3. Sorry, let me check if there is any mistake or not. Oh, sorry, we did it wrong here. So it is 2 into L plus 1 root over S into S plus 1 root over. So there will be root over, there will be root over. So it will be so So it will be 15 by 4 minus 2 minus 3 by 4 divided by 2 into root 2 into root 3 by 2. So they gets cancelled out. So this we calculated it was 4 by 4 divided by root 6. So it is 1 by root 6. So let me add another slide. So cos theta is 1 by root 6. That implies theta is cos inverse 1 by root 6, which is 65.9 degree. So the correct answer is option B, 65.9 degree. I hope this is clear to everyone. Now we move to question number 6. Question number 6 says the landed G factor of the landed G factor for the 3p1 level of an atom is, options are option A 2, option B 3 by 2, option C 5 by 2, option D 0. So landed G factor comes into picture when we consider the total angular momentum, that is L plus J. So like we write in terms, so there is GL mu L. So like that, if you try to calculate the total angular momentum, so it will be the contribution of orbital angular momentum along J and contribution of spin angular momentum along J. So that will give rise to another new coefficient which is called as landed G factor. So what will be the expression for landed G factor? So the expression for landed G factor will be 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2 J into J plus 1. So the complete derivation you can refer to the course lectures. So this is the value of this is the expression for landed G factor, and the label is 3p1. So from 3p1 label we can determine J, S and L, and then we can calculate what will be the value of landed G factor. So I'll give you a few minutes and then we will discuss to get the value of G. So for 3p1, what are the values of s, j and l? So 2s plus 1 is 3, so s is 1, l is again 1 for p, and j is 1. If you put these values, so g will be 1 plus 2 into 1 plus 1 into 2 minus 1 into 2 divided by 2 into 1 into 2. It is 1 plus 2 plus 2 minus 2 divided by 4. It is 1 plus half, which is 3 by 2. So the correct answer is option B, which is 3 by 2. Now we move to question number 7. Question number 7 says the degeneracy, that is the total possible values of Mj of a spectral line 3f, is option A 9, option B 15, option C 21, and option D 25. So here you can see, here it is mentioned what will be the degeneracy, which is basically total possible values of Mj. So here we need to find out the first we need to find out the possible values of J, because here in 3f level the value of J is not present. So we need to find out the value of J. Then correspond to each J values, we have 2J plus 1 Mj values. So corresponding to each J value, we have 2J plus 1 Mj values. So in that case, what will be the total number of Mj values, which is again called as the degeneracy. So degeneracy means it has same energy, since it has same level which was introduced by Bohr. So it has same level, but depending upon the value of Mj, they have different levels. That is the notation. So the different levels which have same energy, but they are mentioned, or they are presented differently, they are called as degenerate levels. So you need to find out the degeneracy. So these are the options 9, 15, 21, and 25, and we need to find out the correct answer. So I'll give you a few minutes and then we will discuss. So what are the values of J. So here S is 1 because 2s plus 1 is 3. And for F, S, P, D, F, so L is 3. So what are the possible values of J? So J will be 3 plus 1 to 3 minus 1. 3 plus 1 is 4. 3 minus 1 is 2. So 4, 3, 2. So corresponding to J equals to 4. 2J plus 1 is 9. Corresponding to J equal to 3. 2J plus 1 is 7. Corresponding to J equal to 2. 2J plus 1 is 5. So MJ, J equal to 4, 9 values. J equal to 3, 7 values. J equal to 2, 5 values. So total 9 plus 7, 16 plus 5, 21. So MJ 21 values. So there are 21 values of MJ corresponding to the level 3F. So the correct option is option C, 21. Now we move to question number 8. Question number 8 says, for single electron with the principal quantum number n equals to 2, the possible spectroscopic terms will be 2s half 2s 3 by 2 2p 3 by 2, 2s half 2p half 2p 3 by 2, 1s half 2s half 2p 3 by 2, 2s half 2p 3 by 2 and 2d 3 by 2. So here it is given n equal to 2 and single electrons. So single electron means S is half. So since n is 2, we will be having 2 L values. So it is 0 to n minus 1. So L will be, so one value will be 0, then 2 minus 1. So 0 and 1. So corresponding to L equal to 0, S equal to half. We have J values corresponding to L equal to 1, S equals to half. We have J values. So for S equal half, L equal to 0, J is half only because 0 plus half, 0 minus half, they are same. Then for S equals to half, L equal to 1, J has half plus 1 is 3 by 2, half minus 1 it is 1 by 2. So for J equals to half, so now there will be labels. So in one level, S will be half, L will be 0, J will be half. So half means 2s plus 1 is 2, L0 means S, J is half, so 2s half will be one label. Then for S equals to half, L equal to 1, J equal to 3 by 2 and half. It will be 2s plus 1 will be 2, L1 means P, then it will be half and 3 by 2. So what are the labels? 2s half, 2p half, 2p 3 by 2. So these are the three labels that will be coming out of the condition where there is single electron and principal quantum number n equal to 2. It will be 2s half, 2p half and 2p 3 by 2. 2s half, 2p half and 2p 3 by 2. Option B is the correct option. Now we move to question number 9. So question number 9 says, the origin of hyperfine spectra is option A, interaction of magnetic moment of orbital electron with the magnetic moment of nucleus. Option B, due to magnetic moment of nucleus only. Option C, interaction of magnetic moments of orbital electrons of different orbits of the atom. And option D, due to spin motion of electrons. So we need to find out what is the origin of the hyperfine spectra. So this is a conceptual question. So I'll give a few minutes to think about this and we will discuss in more details after a few minutes. So hyperfine. One is fine structure. So fine structure is due to interaction between spin and orbital angular momentum of electron, which gives rise to total angular momentum. Now this is hyperfine structure, and hyperfine structure is due to the interaction between the total angular momentum of electron and total angular momentum of nucleus. So it is electron and nucleus J, and this is I, which gives rise to F, which is J plus I to J minus I, like for LS coupling. So here the correct option will be option A, interaction of magnetic moment of orbital electron and magnetic moment of nucleus. So the correct option will be option A. So now let's discuss more options. So the options are due to magnetic moment of nucleus only, no. So only nucleus we need to interact. So fine structure is the interaction between the two angular momentums. So there will be two. We need two angular momentums. So it is only nucleus that is not possible. Then interaction of magnetic moments of orbital electrons of different orbit of the atom. So this is again, this is a part of LS coupling. This is not and LS coupling gives rise to fine structure. And then due to spin motion of electron, so spin motion of electron, again due to spin motion of electron, we got fine structure. It is not hyperfine structure. So the correct option will be option A, which is interaction of magnetic moment of orbital electron and the magnetic moment of nucleus. Now we move to question number 10. Question number 10 says, find the angle between angular momentum vectors L and S for the spectroscopic term 2D 3 by 2. So options are option A 45 degrees, option B 90 degrees, option C 135 degrees, and option D 180 degrees. So these are the four options. This is the similar type of question we have already solved, so that won't take much difficulty. So I'll give you a few minutes and then we will calculate what will be the correct option. So we have already solved this type of question. So the angle theta will be cos inverse j into j plus 1 minus s into s plus 1 minus l into l plus 1 divided by 2 s into s plus 1 l into l plus 1. So for 2d 3 by 2, 2s plus 1 is 2, that implies s is half, j is 3 by 2, l is d, that means l is 2. So theta is equals to cos inverse j 3 by 2 half 2. So 3 by 2 into 5 by 2 minus half into 3 by 2 minus 2 into 3 divided by 2 into half into 3 by 2 root over into 2 into 3 root over. This is cos inverse 15 by 4 minus 3 by 4 minus 6 divided by 2 into root 3 by 2 into root 6. 2 2 gets cancelled out. Cos inverse 15 minus 3 minus 24 divided by 4 into 1 by root 18. So cos inverse this is 24 minus 12 divided by 4 into 1 by root 18 means 9 root 2. 3 root 2, sorry. So it is cos inverse minus 1 by root 2. So 4, 3, 3 gets cancelled. So it is minus 1 by root 2. So theta will be 135 degrees. So the correct option is option C, 135 degrees. So similar types of question we had already discussed. This was the formula to determine theta between L vector and S vector, and using that formula we can easily calculate what will be the value of angle between L vector and S vector. So with this, we come to the end of today's interaction session. With this, we come to the end of today's interaction session. Uh, I would like to thank you all for joining in this session, and I hope definitely this question will help you in solving your course assignments as well as the questions that you must be facing in your exams. So in the next interaction session, we'll be solving a few more questions based on the concepts covered on week 5 lectures. Till then, I hope you will be interacting with me more in the future interaction sessions. With this, I end this interaction session. Thank you so much.